Do you think the screen was frozen? It wasn't. That was just me pretending to be a statue. Okay. So this week we're doing Charles Law problems. Okay. Last week the Boyle's Law problems did not go that well. Okay. I think it's probably because a lot of you guys didn't watch the whole video and do the practice. So I really encourage you to watch this. I know it's going to be a little boring because it's me doing two math problems, but if you combine that with watching the other video and then doing the practice, I think you'll be able to get it because it's not. It's just like 2 to 3 steps of algebra, okay, which I know all of you can do. So in the other video, we talked about Charles Law, the relationship between volume and temperature, okay? It's a direct relationship. As one goes up, the other goes up. If we heat up a balloon, it gets bigger. If we put a balloon in the freezer, it gets smaller, right? Here's our formula this time. It's V1 over T1 equals V2 over T2. Now, since it's a direct relationship, it's set up like this. If you remember, Boyle's Law was P1, V1. They were next to each other. That's because it's an inverse relationship, which meant as one goes up, the other goes down. Here, one up, one down, or one up, the other up. One down, the other down. Okay, so how do I solve this? Same thing, I'm just plugging in. So our problem says a balloon with a volume of 1.5 liters is in a room with a temperature of 300 Kelvin. The balloon is taken outside and the temperature decreases to 280 Kelvin. What is the balloon's new volume? Now you're saying, that's a lot of words right there, Snellman. And I'm saying, yeah, it is. But that's okay because we don't really care about any of those words except the part where we have our numbers. A volume of 1.5 liters. That's going to be my V1, 1.5 liters. In a room with a temperature of 300 Kelvin. Temperature of 300 Kelvin. These are my V1, T1 because these are my first set of conditions. Now, I know that Kelvin is a temperature, right? The temperature decreases to 280 Kelvin. What is the balloon's new volume? Okay, so I know that this volume is going to be lower than this volume. How do I know that? Because my temperature went down. If my temperature goes down, my volume goes down. So let's plug it in. V1, right? I'm basically taking it up and I'm setting up this proportion. V1 is 1.5. Again, I'm not going to bring my units over just because it's a little bit cleaner, all right? Over here, this is a decimal. Over here, 300, that's T1. That goes on the bottom. V2, X, 280 is my T2. Now, how do I solve this? Well, how do I solve it? I'm asking you. What do you think? If you're saying cross multiply in your head, you're 100% correct. So let's cross multiply. 300 times X gives me 300X. 1.5 times 280, that gives me 420. Now, I have to get this X by itself, so what do? I divide both sides by 300. Those 300s cancel out, and I'm left with X equals 1.4. Okay? Now, it's a volume, so V2 equals 1.4. What unit is it? It's liters because my volume up here is liters. So 1.4 liters, right there is my answer, okay? So that's the first problem. Again, take my volumes, plug them in, I cross multiply, and I'm just solving for X, okay? So that's problem one. Let's do another one. All right, our second problem up here. says if a sample gas occupies a volume of 125 milliliters at 300 Kelvin, what will the temperature be if the volume increases to 200 milliliters? Now, there's something you got to take into consideration. You have to remember is that our temperatures when we solve these problems always have to be in Kelvin. Now, if we were in school, we would be giving you these temperatures in Celsius and forcing you to convert to Kelvin. But we're taking it easy on you guys, and so we're giving them to you in Kelvin. The next set of problems we solve will be Gay-Lussac's law. Yeah, his name was Gay-Lussac, right? Worst name ever, but that's okay. Anyway, and those problems will also have to be in Kelvin. Again, we'll probably give them to you there, not requiring you to change. Just because we're trying to keep it simple and helping you guys just focus on the big pictures and big concepts here. Okay, so let's do it. Sample gas occupies a volume of 125 at 350 Kelvin. We know that Kelvin's my temperature, so T1 is 350 Kelvin, 125 milliliters. Okay, it says, what will the temperature be? That means temperature is unknown, and my volume is increased to 200 milliliters. Another thing to consider here is that we're assuming other variables stay the same. We're assuming the number of moles, the amount of molecules stays the same, and we're also assuming that the pressure stays the same, okay? All these variables are interrelated, and so when you're only solving for two of them, you're under the assumption that the other two remain constant, remain the same. So let's plug this in, okay? Volume 1, 125 over 350 V1 T1, okay? V2 T2 is X. Again, I am cross multiplying. And just because it just makes me happier, I always put the variable on the left-hand side. You don't have to, but that's the way I like it. 125 times X is 125X. 350 times 200 is 70,000. To get X by itself, I divide by 125. Cancels out, cancels out. I'm left with X equals, what was my answer? Let me make sure I wrote it down. 560. 560. So T2 equals 560 in my unit for temperature. Always Kelvin, okay? Always Kelvin. I know this work is a little hard to see here because I got my little mini whiteboard, but it's the best I can do. If you don't understand what I've done, go look at the YouTube video, all right? And I also encourage you guys to come to office hours if you're having questions. If you watch these videos, please do the work before the office hours, if at all possible. It's not a requirement, but it just allows me to help you. If you do come to office hours, you can come with questions, okay? That's all. Those are solving Charles' law problems.